So I'm going to start today by telling you about my background as a computational scientist, an area where I spent a decade partnering with scientists in areas from particle physics to molecular biology. I work with those scientists to develop the computational models, systems, and simulations that allowed them to advance the boundaries of human knowledge. So this is a personal story. It's a story about insights and discovery, about numbers, computers, math, and science. And most importantly, about the people who work together to achieve great things. There's only one takeaway from this talk, and that's that success comes from teamwork. We're going to return to this throughout the next 30 minutes. While it might seem like a truism, the reality is that for a long time, analytics of various stripes has consisted of individuals working away in an assembly line fashion, taking inputs from the person before them and outputting results to the next person. In my career, I've used software such as Excel, Perl, and MATLAB, outputting spreadsheets, PDFs, and PowerPoint. I imagine many of you have been the recipients of the kind of work I've produced in the past, appreciative for its completeness and insights, but unsure how to engage in a conversation to improve or adapt the results. Or worse, unable to recreate and extend the results quickly and easily the next time a similar situation arises. The presentation I'm giving here is available right now at this URL if you want to follow along. It's also going to be posted in the post-event website once we've produced the videos and for all the material. But for people who like to follow along, which is what I like to do, you can grab it there at bit.ly/ac17-collab. So this is my electrical engineering class Mud Bowl team from 1996. See if you can spot me. I played football for 7 years, and it shaped me as a person and my ideas about hard work, teams, leadership, and understanding how each person has an important role to play for success to be possible. I spent the last 20 years of my life working on large-scale data analysis and computational science problems. And there's never been a time when there's been more opportunity for teams of people, each bringing their own skills and insights to the game, to be able to do amazing things together. So if there's a footnote to success comes from teamwork, it is this. Teamwork in data science means bringing together individuals with different backgrounds and abilities who are able to collaborate in real time, rapidly iterate their analysis, easily reproduce their results, and scale their work from laptops to servers to clusters. I believe open data science is the only way to do that. So, let me start with where I am today. My name's Ian, and I'm, today, a product marketing manager at Continuum. I've spent a long time considering myself a computational scientist. But as I've worked at Continuum, my role's shifted to helping people like you figure out how you can best leverage open data science to be successful as an individual, as a team lead, or organizationally. And in that role, I've come into this position as a marketing manager for our products. I'm a passionate advocate of open data science. I'm passionate about the opportunities that it provides and the way it enables people to do great things. And I consider myself an educator and an evangelist for the use of Python and also Anaconda. I spent many years at Continuum as one of the lead trainers, doing corporate training for the use of Python. Prior to that, I was a lecturer at Harvard in the computational science and engineering program. My first taste of big data computing came during my master's degree 20 years ago at the University of Waterloo in Canada. It's funny to say, but today I think I understand this better than I did at the time. I don't think there's many students, master's students, who could say that. I think mostly it's a mark of how lost and confused I was during my master's degree. These are some images from my master's thesis, where what I was working on was the development of hidden Markov models, HMMs, that could be used to predict words in continuous speech recognition systems given a parameterized acoustical model. This is a pretty standard kind of technique. This is what happens today on your phones and all sorts of speech recognition systems, where you're trying to predict the likelihood of a particular word given a set of observations. Now, how do these systems work? In this case, we were building what are called triphone models, where you have parts of speech, and you characterize that particular part of speech by the part that came before it and the part that will come after it. You then have a dynamical parameterized model, statistical in that each of the parameters have a Gaussian distribution. And so those 100,000 acoustic triphones that you're trying to model have about 100 parameters each, which gives you about 10 million parameters to estimate. Additionally, you want to adapt those models in real time as you're bringing in the acoustics. What's fascinating to me is that in 1999, we were actually able to do this pretty darn well. And it's taken 15 plus years before that technology has really been successfully adopted in the mainstream. The computational part of training these models and then actually running them in an operational system is pretty tricky. So this was my first taste of big data computing. Several years later, I had the great privilege to be part of a CERN project, the LHCb project's computing team. And I did my PhD as part of that computing team. So CERN, for those of you who are familiar with it, it's a large underground accelerator ring located on the French-Swiss border outside of Geneva, Switzerland. It's about 30 kilometers around. It's about 100 meters underground. And there's 4 detectors around the ring. LHCb is the baby detector. The baby detector means there's only about 500 physicists who are working on LHCb. The computing team consisted of about 15 of us. We are developing a distributed computing infrastructure for thousands of concurrent users. Once the system was operational, there were going to be physicists around the world who were going to be leveraging and utilizing the data coming off our detector, who are going to be analyzing it and processing it with the computing infrastructure that we put in place. That meant that we had software that was going to be running in hundreds of federated computing centers in a coordinated fashion to process this data, with no centralized control. We need to be prepared for over 1 million servers where the software might be installed. For a project that was going to have a 20-year lifespan, producing 20 gigabytes of data a second, 14 hours per day, 7 days a week, 7 months of the year. So how do CERN physicists do this? There's some pretty smart people over there, people who brought us the web, HTTP, and HTML. It's no surprise that those things came out of this massive scientific collaboration, globally distributed. They needed to be able to effectively communicate with each other. And so they had been utilizing, through the 80s and early 90s, things like FTP and Gopher and news groups and so on and so forth. When Tim Berners-Lee worked on HTML and HTTP protocol, he was doing it to facilitate collaboration. He was doing it to facilitate what we call today data science, sharing of data, data analysis, data visualization with other collaborators. That was where the web was born, at CERN. These same people, a decade later, were trying to figure out how to do this with orders of magnitude new data, but not at the level of human collaboration, at the level of computational collaboration. How do we federate and share these systems, computers? Dealing with multiple petabytes of data per year, these big teams, and where the computational part isn't just a nice to have, it's a critical piece. There's no way to make sense of the data or discover new physics. I think this is one of the best ways to visualize the kind of computational challenge that these guys are facing. This is the Endcap, the calorimeter Endcap of the Atlas detector. It's got millions of wires coming out of it for every single calorimeter sensor there is. Millions of those wires with a 40 megahertz data rate, signal rate, as it's operating. And that's just one component of one detector. You can see a bit of a ring at the top there. There's a thing called a silicon vertex detector that goes in there that has a similar number of sensor elements to what we're seeing from the larger calorimeter ring. So how would you do it? This is what the CERN physicists do. They develop custom hardware. This is the CMS level 0 muon trigger, custom integrated circuit. So for the fastest on Detector data processing, they write their algorithms into hardware. And they're not using FPGAs, they're actually cutting their own ICs, and that's their level 0 trigger. Today, what do we see? In critical applications, people are using this sort of technology, custom hardware. They make use of giant compute and storage clusters. And today, we're all familiar with these sorts of things. This is the CERN Computing Center. They write wicked fast algorithms in Fortran and C to get the highest possible performance out of the core numerical routines that they're performing for the software that they're writing. But then the last piece is that they use Python, pun intended, as the Swiss Army knife for computational physics. Python is used everywhere at CERN as a component to allow them to have interfaces on top of those Fortran and C algorithms, to create the infrastructure, to create the applications, to provide the pieces that glue together what happens behind the websites and the web services, to provide the command line tools and the things that are run on clusters. Python is very widely used at CERN. But in 2002, as a professional software engineer at the time, I'd spent 3 years at a tech startup, when I joined this computing team and I discovered that this group of particle physicists, remembering I'm coming from an electrical engineering background, were planning on using an interpreted, dynamically typed language to write an application that was going to run on millions of computers for 2 decades with thousands of users for this massive distributed computing infrastructure, I thought they were insane. I had no idea the power of Python at the time. Of course, those smart physicists, they knew exactly what they were doing. They knew the power of Python, and they knew what it could deliver for them. Python's provided a lingua franca for data science. It's human readable. It's easy to learn. It's object-oriented. Cleanly wraps C and Fortran. And there's an amazing foundation of high-quality data science libraries. Of course, we're here at AnacondaCON. Anaconda encapsulates and provides a large set of those, but with a much deeper bench for the specialized components that you need or the innovative components that are coming out every day. And it's suitable for the small tasks like scripting and algorithms, or for bigger things like large data processing pipelines, or even in developing applications, whether they're web-based applications or rich GUI applications. You can tie all of these pieces together with Python. What do you have when you don't have that lingua franca? You're stuck with your Tower of Babel problem. You have some people writing Fortran, some people writing C, some people writing bash scripts, other people in Perl. And then how do those pieces interface? How do they come together? How do you go from little exploratory pieces where individuals have gone off to do their own piece in their own way, to then come together to create that bigger thing, to achieve that bigger organization or project objective? Without something like Python as a common glue, as a common language, as a common enabler, you're stuck. People can't understand each other, and they can't work together. It's necessary to have common idioms, tools, and systems to facilitate communication and collaboration. So, let me tell a story, briefly, one slide. Newton and Leibniz were 17th century Renaissance thinkers. They concurrently established the foundations of calculus. How concurrently is a matter of some debate. They established it to describe and analyze dynamical systems. History suggests that Newton used his influence to be credited as the creator of calculus at the time. However, ultimately, it's Leibniz we have to thank for the foundations of calculus as we know it today. Why is that? Because it was only with Leibniz's clear notation and presentation of calculus that the world was able to benefit. In contrast, Newton's calculus was esoteric and inaccessible. But sometimes esoteric is okay. And I'm not kidding when I say that. Sometimes it is. So let me tell you about hermits and high priests. Data hermits work independently and have no accountability to anyone else. They can happily seclude themselves in a cottage off the grid and do their own thing in their own way. I won't deny it. Sometimes this can be a path to innovation and enlightenment, but it can also be a path to isolation and perhaps failure. The data high priests have established universal rule over data modeling and analysis. Their power comes from their control, and they exercise it behind closed doors. Few are admitted to the priesthood, as they guard their skills and responsibilities jealously, but in return deliver quantitative insights as the moons and seasons change. Of course, these are both caricatures, but I'm sure we've all seen aspects of the data hermit or the data high priest in people or organizations we've worked with. I have to admit, I've been the data high priest myself, where I've had my own set of tricks and tools and scripts and techniques that I use to get my job done for others. There was no way anybody could reproduce what I was doing. So let me carry on my personal story. After I completed my PhD, I spent a year at a French research institute working on models for parallel distributed option pricing before moving to Harvard Medical School and joining a structural biology lab that wanted to improve their computational techniques for protein structure determination. Here we're looking at a molecular dynamics simulation of the OGT enzyme, common in mammals. It acts as a nutrient sensor, and it's involved in signaling metabolic behavior. That might not mean a lot to you, but probably metabolic behavior is meaningful, and we're mammals, so it's important. OGT's role in metabolic regulation means that it's linked to diabetes, neurodegenerative diseases, and cancers in cases where it misbehaves. I was not directly involved in this work, but my colleagues who were spent collectively many years working to determine the 3D structure, the 3D molecular structure of the OGT enzyme in order to better understand its behavior. My contribution was just, in this particular case, was just to construct the molecular dynamics simulation and produce this one particular animation. In general, it takes about 3 to 9 months in the wet lab to prepare a protein sample. Once prepared, it's only a few days to image those samples and produce digitized representations. They make use of techniques that we're all familiar with in our own way, believe it or not. They use X-ray crystallography techniques, so they shine X-rays at the protein crystals, which then provide a diffraction pattern. And from that diffraction pattern, you then get to work backwards to what the protein might have looked like. They use nuclear magnetic resonance imaging, and they also use cryo-electron microscopy. 3 different techniques. They're all different imaging techniques, but they follow the same kind of pattern. A long time to prepare high-quality protein samples, a relatively short period to image those, and X-ray crystallography is a destructive imaging technique. You wipe out the crystals when you shine the X-rays through them. So you better get some good data from it. But those images aren't yet 3D atomic models, not in any of those cases. You need to then work backwards from the data that you've collected to create those 3-dimensional models. And that can take from weeks to months to complete for a human being sitting behind a computer. Sometimes teams of them, but often a single person managing the data they've collected to reconstruct and analyze it to create those sorts of models. You might know this as protein folding. So the question that my supervisor was asking when he got me on board as a postdoc was, how can we accelerate the time to insight? How can we accelerate this process? How can we process the data faster, reduce the computational time, and improve the quality of the results? And again, the answer comes back to the key takeaway of this talk. Success comes from teamwork, bringing together biochemists, data scientists, software engineers, and IT system administrators. It's possible to tackle these challenges, and these are important challenges. You guys have your important challenges, and this is my story of my personal challenge that I've been facing. This was just one of many projects that I worked on, this particular OGT one. I only had a small role in that one. But the pattern of how do we do these things is a large open challenge. There's thousands of structural biologists around the world trying to understand the basics of the biological mechanisms in our system at a molecular level, molecular biochemistry. So the title of this talk is Data Science Team Collaboration. Forget about meeting me halfway, take me the last mile. We can ask, what does halfway look like? And I should say, before I go through this, that halfway is a great start. So don't feel badly if the following represents your reality. So for today, a good data science environment would look like high-performance computing resources, for example, a Hadoop infrastructure, with a wide selection of the most popular analysis software. At Continuum, we have a number of different arms of the company. We're not just a software product company. We don't just do software engineering and product development and open source data science software. We also have a very active, vibrant consulting wing, and I hope you've had a chance to talk with some of my colleagues. Michael Grant and Peter Steinberg actually are one of the demo kiosks showing off some of that, that work. When we go in to a lot of our clients, the environments they're setting up look like this, where they deploy a very wide range of data science software. And they then leave it to the data science teams to kind of experiment and explore in these data lab environments. An organization might provide training and documentation and technical support. It's kind of an outline about what meeting somebody halfway looks like. But where does this leave our biochemist? It leaves them like a fish out of water. Why do we want to take an expert biochemist and force them to be a software engineer, an IT system administrator, a statistician? What can we do to let them focus on being a great biochemist? And of course, you can swap biochemist for business analyst or any other person or role that you can think of. Back to success comes from teamwork. And an important comment is that teams don't equal teamwork. We can all appreciate that. Success doesn't just come from a team of people with different skills. It comes from the team being able to work together collaboratively in real time to iterate, each person applying their expertise. So, this is what it means to go the last mile. Having a DevOps engineer who's able to pre-configure computations that are scalable so that you can easily go from the laptop to the server to the cluster. The DevOps team or the DevOps engineer is a partner, not a service provider. A software engineer who can create customized software for the task, project, or individual, avoiding generic static software setups. Data scientists who are able to compose workflows. And an analyst who's provided with simple high-level interfaces with options to drill down into the details when they need to. So let's go back and say, what about those proteins? So let's apply this thinking to this particular problem I brought up for my last stage of my computational science work. It normally takes about 10 to 200 hours of computing time to match a template protein fragment to the imaging data in the case of X-ray crystallography, which was the domain I was predominantly working in. There's 100,000 templates, known protein folds, to choose from that are available today. We could say, let's just be stupid and try them all. Sometimes you'll be surprised. But you can do the math, and you can see the computational challenge this presents. So this seemed like a crazy thing to do. I kind of cut to the conclusion of this, but we actually showed that it had some really good value. And if it was easy to do it, and if the computing time was available, why not do that? So I spent 18 months working with biochemists and IT sysadmins across the country to create a sensible parallel and distributed computing workflow. It then took 4 to 40 hours on the clock, wall clock time, so between like half a working day to maybe 2 days, to run 2,000 to 20,000 hours of parallel computations, which is about 2 years of computing time, with real-time updates of the results and a web-based interface to give people access to the outputs. The analysis was performed in Jupyter notebooks, so the workflows were stamped out in Jupyter notebooks. And that then allowed the biochemists I was working with to customize and rerun components of those. That's not the 20,000 hours of computing. That's once you've done that computing and you've got kind of your analysis of the final results, you could then tweak those notebooks individually and rerun your own report, your analysis report for your particular data set. And using a file system-based drill down. We were doing 6 million hours per year, which is about 700 years of computing every year for several years in a row, with peak parallelisms of over 20,000 cores, running at about 50 computing centers across the United States. And here, we've got a data science pattern that's established. I'm going to be connecting this to Anaconda, but this point here is a whole talk in one slide. So I'm going to go through it in just a few bullet points. This is a checklist for you and your projects around what do your data science projects look like, how are they initiated, and how do they work. How is the project you're taking on? How are they done today? What are the opportunities for improvement? You then go and prototype and evaluate, see if they're better, rinse and repeat. iterate quickly with that team of people. Standardize and automate a small-scale workflow or model, and then scale that workflow. What does scaling mean? More data, more computers. Process bigger sets. Pre-process and distribute the data to facilitate what you're doing. Instrument the execution, so you then have quality metrics you can use to understand whether your data quality is off or your model is misbehaving or poorly performing for the new incoming data sets. Establishing easy access interfaces then puts it in front of the end users who it's meant to benefit most. Avoid establishing a new high priestdom. Make the resources that you're creating available to people. Once you've done that, then these things you've created can have their own programmatic APIs, RESTful APIs or direct language-level APIs. And those pieces mean that that model or workflow you've built can become a subcomponent of the next advanced model or workflow. And again, success comes from teamwork, but the footnote is that the teams are collaborative cross-functional teams. I'm going to put in a really quick comment here for breaking data science open. I said this was a whole talk in one slide. In fact, there's a book that O'Reilly's going to be publishing in the next month or so that a few of us at Continuum have written called Breaking Data Science Open, and it touches on many of these topics, so look out for it. I'm going to finish now with a quick run-through of 3 steps for how you can adopt Anaconda to enable team-oriented data collaboration. I heard Continuum's founder, Travis Oliphant, give a talk at Supercomputing in 2012 where he described the vision for Continuum. It was a vision of collaborative, web-based, open data science. It was the embodiment of what I had spent the past decade doing on a one-off basis in computational physics, computational finance, and computational biology. I was hooked, so I left Harvard a few months later and joined Continuum to help make that vision a reality. It's really exciting to be here today because I joined Continuum when there were about 15 of us. There were fewer people in Austin than there were in the rest of the world. And here we are today at AnacondaCON, where we're able to see the impact of the commitment that a group of people made and then a community who came together to support and help amplify and echo that effort and what we've done. So you've heard a lot about Anaconda this week, and I hope you've taken time to speak with my colleagues for providing the demos, the product, the platform, the larger ecosystem. Here are the last 3 steps for what you can do to be able to make use of some of these techniques I've tried to describe around how success comes from teamwork for data science. Step 1 is Anaconda. Anaconda provides 200 of the most amazing tools and libraries for open data science. It's a gateway to open data science, but it's designed for a single user on a single system. It gives you access to some really popular applications through its graphical interface, the ability to create your Conda environments with just exactly the versions of software that you need, and the notebook-oriented computing model, which many of us know and love. Very powerful, very impactful in terms of the way it brings together data, code, story, visualizations. And I'm going to go through these slides quickly since I'm at the end of my time. Step 2 is leveraging Anaconda Cloud. Anaconda Cloud is a place where you can pick up third-party, packaged, curated components to augment what you get with the Anaconda distribution. There's R packages there. There's Python packages there. We've got about half of PyPy is mirrored as a Conda package. We've got hundreds of R packages available as Conda packages, so they're easily installable without a full compiler chain on your local system. And then there's community-contributed channels, such as Conda Forge, which has a rich group of people around it. And right now, you can in Conda install TensorFlow for Windows, Mac, and Linux. The part B is My Anaconda Cloud. And that you can make use of Anaconda Cloud not just to pull down other people's assets, but to actually publish your own work, to create your own Conda packages of things that you've created or things you've compiled in your own way, or of your notebooks. And here I just have a few images from my space, anaconda.org/IJStokes, showing off places where I've published talks that I've given or notebooks that I've been working on for little projects. And it goes beyond that to see a number of data science packages that I've created and a little snapshot of what it looks like. When we say a Conda environment is compact, it's less than a kilobyte to specify a full computational environment. We're not talking about megabytes or gigabytes for snapshots of containers, about 300 bytes of code. And finally, Anaconda Enterprise. Anaconda Enterprise takes those capabilities for the individual user or the connection of the Anaconda Cloud Conda package repository, and it makes it available within your organization. So teams of people can come together to access a common centralized computational infrastructure. They're able to simply use a web browser, or if they prefer, they can SSH in to the organization's internal system to get all of the software that's already there, the data that's already there, using their standard accounts, and have access to those things through the web interface or through the standard system. And coming soon, as you've heard, is our version 5 of Anaconda Enterprise with even more capabilities, providing a Shiny server, providing the ability to deploy bouquet apps, and have running services. So we've said in the past that Anaconda is designed to give superpowers to people who change the world. Today I want to tell you that Anaconda gives superpowers to the teams who change the world, because that's where real success comes from. Thank you.